So we've talked about how sound works with the sound pressure waves that move the air molecules back and forth through some sort of compression and then rarefaction, where those sound molecules hit our eardrums. The eardrums capture that energy and then move it into the cochlea, into the ear, where we have fluid that vibrates. The basilar membrane then starts to resonate with the various ratio vibrations, which then sends electrical signals into our brain and we hear sound. So let's talk about how we're going to capture that same physical energy into an electronic device to convert that electrical energy into sort of an analog of electrical energy. So electrical energy will then allow us to send it to cables, into a mixer, and eventually we'll convert that into a digital representation, which would be how the computer records that same information. So the way we convert physical energy into electrical energy is through some kind of transduction. Most of the transducers that we are familiar with are called microphones. So what I want to talk about today is the several designs of microphones that you may discover, and what kind of use our best applications are used for those microphones. So let's talk about how microphones work. There are many different design microphones, but I want to talk and focus on two primarily today. The first one is a dynamic microphone. And this is perhaps the most common microphone that you will discover. The dynamic microphone works under this principle. So if we see a dynamic microphone, we will see a membrane covering the top of the microphone. Usually this is going to be polyvinyl chloride or some other kind of thin material. This membrane, or this diaphragm, will move according to the air pressure, the sound pressure waves that hit it. We'll start to move that diaphragm. That diaphragm then, which you'll have inside here, is a copper wire, that moving coil, and around that will be a magnet. And then the magnet obviously has a positive and a negative charge to the magnetic energy. As this diaphragm moves that coil of copper, then as the copper moves closer within that magnetic field, it will then send a positive and negative energy electrical charge out the cable. So what we've got is a conversion of the electrical energy, or the acoustic energy, into an electrical signal, which will then convert us into patterns of alternating current. As you know, electrical energy, we'll be talking about alternating current and direct current. So direct current is something we can't represent sound in direct current, but we have to have something that alternates to be an analog for the alternations of compression energy in the airwave form. So the dynamic microphone is the most common design that we will find. It's also the microphone principle that how speakers are made. When you have a speaker, it's the same idea. You have a cone which is moving, and you have a moving coil around a magnet, and then as the electrical energy moves that magnet coil, it moves the diaphragm, which moves the air molecules again, and we hear the sound. So in some ways, the transduction in a dynamic microphone and then a speaker is the same technology. We're just reversing the process of those. So dynamic microphones are most common. One of the perhaps most common design of that is a company called Shure, and they make this is a dynamic microphone. This is actually a SM77. One of the most common ones is the SM58. It's a vocal microphone. This is the instrumental version of that. But you've seen this microphone perhaps everywhere. They're inexpensive. They're very durable. This design is very hard to damage this microphone. It can be damaged, but it takes a little bit of energy to do that. So when you see a singer on stage who has the microphone directly against their mouth and they're screaming into the instrument, the diaphragm is able to take that energy and really not damage any of the inside technology. So this is a very durable microphone. It has a lot of applications in sound reinforcement. So the dynamic microphone is the one you probably, if you don't have a microphone, this is the one I would recommend you consider taking a look at getting, because you can use this both in recording studios as well as for sound reinforcement, which are the two primary applications that we'll be talking about in this course. The other kind of microphone is a condenser microphone. It has a different kind of technology on the condenser microphone. The condenser, how this works is you don't have a magnet to give you the polarized electrical patterns. You have two plates at the top of the microphone, and one of them is going to be charged to a positive electrical energy, the other one will be negative. And the difference between those two is called capacitance. So we call this sometimes a capacitor condenser microphone. Other times it's called electric condenser. There are various versions of this. So what we have to do, we have to pre-charge each of these plates. And the plates are very thin. Often they're made of platinum or gold, very thin gold. And so we have to have some kind of external power source in order to pre-charge those plates, one to positive, one to negative. So as the air pressure pushes down on the top plate, it pushes it closer to the bottom plate, which that then creates a capacitance difference. Over time, that distance is then captured and sent out to our cable, and we get both the positive and negative electrical energy going out to the alternating current again. So the trick on the condenser is we have to have some kind of power source to pre-charge those plates. This can be done several ways. You can actually have a battery on board with either a 9-volt battery or some kind of NiCad battery. For example, here is a condenser microphone that's made by Equitech, and this part right here is the battery. So we pre-charge the battery with this NiCad battery so that then the plates that are inside this housing down here are constantly charged. I'll come back and talk more about this microphone in just a second. Here is another condenser microphone. This is an AKG C414, which is a very classic microphone. This does not have a power source on it. So when we plug the microphone cable into this, which we'll get to cables in just a second, the microphone cable has to go somewhere where the charge can actually be sent into the cable. That's called phantom power. Phantom power was first developed by really the German microphone company called Neumann back in 1966. They were working with this idea of this condenser technology microphone, and they worked with the Norwegian broadcasting company and came up with a standard that was standard there, which was a 48-volt phantom power. So because of that particular relationship, the 48 volts has become the standard for most phantom power. So we can either have an external phantom power source, but most mixers, which we'll be talking about in just a second, most mixers come with a phantom power source built in. So there's usually a switch on the mixer where you can turn on the phantom power if you are connecting a condenser microphone to your mixer. And we'll demonstrate that in just a second. So in the condenser structure, this particular technology is a little bit more fragile than the dynamic microphone technology. It has, because of the thinness of the plates, the delicacy of it, it is not something you will see as common in sound reinforcement applications. If you take a condenser microphone and you have someone sing or yell very close to it, you could potentially damage those plates, bend the plates, and you would lose the sensitivity of the microphone. You would never put this microphone against a bass drum or any kind of very loud sound source because the damage would be too much for that. But these are much better for recording purposes. So when we talk about a microphone, we've got several things we have to consider in which microphone to use for our particular purposes. There are other things we need to talk about that are the variables of microphones. One is the technology of dynamic versus condenser. That's the primary thing. Dynamic, you'll find more in sound reinforcement. Condenser, you'll find more in studio recording applications. But you can find both in either. Another variable of microphones has to do with called polar pattern. So if I look at how the microphone is sensitivity to the direction of sound coming into the microphone, we call that the polar pattern. And there's some standard variants on that. If we have a microphone placed here and the sound is equally picked up in all different circles, we call that omnidirectional. So an omnidirectional microphone you would have in a situation where you need sound coming from all 360 degrees and equal energy coming into that, and it would pick them all up. Right here is something called a boundary microphone. A boundary microphone is an omnidirectional microphone. Usually you'll see these if you're in a conference room or some kind of application where you need to be able to hear everybody in the room. The boundary microphone will be an omnidirectional. This is a different kind of technology. This is a PZM technology, which is not particularly what we're interested in for sound reinforcement applications. This would be more for vocal applications. So the omnidirectional is the one that you'll find some microphones will have that capability. Let me show you on my AKG. If you can see right here, there's a switch on this microphone which allows us to switch to the various polar patterns. So this one you can actually change from the omnidirectional to a cardioid pattern. A cardioid pattern is going to have a different kind of pickup pattern. So a cardioid will give you sound in front of the microphone, in this case is this direction, will be the front of the microphone, and some of the side energy coming in. So if you were to, like this one is also a cardioid, but here the front is facing this way. So when you see two singers that come side by side, you want to sing into one microphone, you've got to have some width to how the sound sensitivity picks up. So that way you can have two vocalists close to this, it would still pick up their energy. But if I were standing on this side of the microphone, you wouldn't hear very much coming in because this cardioid pattern limits the sound coming in from one direction. So the cardioid is the most common. Now there are lots of variations of this cardioid pattern. You can have hypercardioid or supercardioid. What those do, they narrow the energy field more as you get in front of the microphone, and usually the hyper and supercardioids will allow some energy directly behind to come into that. So those would be for particular applications where you don't want exclusive sound coming in, but also you want some of the resonance of the sound bouncing off the back wall or some of the ambience of the room sound to come into the microphone. So depending on what you're recording or your sound application, you would choose one of those cardioid patterns. So in order to have a versatile microphone, and the more expensive microphones will give you this shifting. There's one more that's called a figure 8. A figure 8 is a sort of a double cardioid. What it does is allow for sound energy to come in front of the microphone and also equal energy to come in behind the microphone. Figure 8 is a very useful pattern that you would be using for recording. You wouldn't be using figure 8 on sound reinforcement. Usually sound reinforcement will be using only a version of cardioid. Another specialized microphone is referred to as a shotgun microphone. So this is a Sennheiser shotgun microphone. You'll often see these in video or film applications where there'll be someone usually with some kind of pole and they will have a shotgun microphone. And what this does is a very narrow cardioid pattern. It allows for a pickup of only a tiny range of area, space area. So you can point this particularly at someone far away and you will get nothing but that sound and it will cut out any sound around that. So if you ever watch sports games, soccer, football, whatever, then you'll see often if you're listening to the sound of what's happening in the field, it's usually done with a shotgun microphone that's pointed toward a particular player to pick up what's going on in them. So these are the primary design polar patterns that we're talking about. When I come back, we're going to talk a little bit more about the cabling and some other variables, which is impedance, other things we need to know before we get the microphone going into our mixer, which is where we're trying to get to.
The preceding program is copyrighted by Emory University.